Save me for the rest of the semester. Oh, wait, we don't want to do that again. Do you want to go back to Monday and the balloons? I do not. Let's go to Wednesday. All right. So yes, there we are. Oh yeah, mini quiz time. So it's time for our free quiz. Technology away, phones off the table, funny watches away, computers away, but you can speak to whoever you want as usual about this discussion quiz. I think this is my favorite part of the week because I can see you all discussing problems very actively.
This would be true. I true 0-1 is so
Pretty sure it'd be
How about you two? You talk to other people, you want other people, have to only have two. Right. Good night. Probably.
Yeah.
Who needs one more minute? One more minute? Are we good? Oh, we're good. Okay, hand them up, please. Do I have, oh, there's. All right, thank you. Do I have them all now? Okay, what do we think the answer is? C. Let's find out. We think it's C. I don't have a real pen today. I only have this highlighter. So that's what we got. Well, first, let's just see that that's false. The instantaneous, what is the instantaneous rate of change? No, but like in general, like what am I talking about? It's the slope of the function at that point, right? It's the slope of the tangent line. So at -1, I apologize that I don't have a real pen, but can you see that yellow line that I drew here? Here's the tangent line, and the slope of it is clearly not 0. Okay, so this one's definitely the false one, so you're all correct. For the other ones, I just want to point out that for A, when we say the instantaneous rate of change is positive on an interval, that means for every point on the interval. So not including 0, because the instantaneous rate of change is 0 there, but everything after 0 and going up to 1, those slopes are positive. And then for the second one, so it's that. We're looking at the interval from -2 to -1, and that's these slopes. And those are all negative. And then finally, instantaneous rate of change is 0 at x equals 0. We're at this point, which has slope 0. Okay. So instantaneous rate of change, or I heard people saying IROC over there. I say that too. The IROC of the function is the slope at a point. Yeah.
So
Well, we don't know yet. That's what we'll do today, right? So we know what it is, right? And we can look at it and say, okay, it's 0. It's a fantastic question because, well, that one's pretty obvious, but this one right here, like, it seems like it's a negative slope, but what if I wanted to compute it? Like, I only know 1 point on the line, so it's not clear how I would compute such a thing. So let me see if I can figure out how to make this go away. Success. Okay, we'll pick it up from here. Oh, here's a leftover question I didn't get to last time. This is a really good question. If you can't figure out the right answers and you have a blank quiz, you should ask. So go to Piazza. You can ask me on Piazza. People have already been asking quiz questions on Piazza. You can go to Learning Center. You can go see Jerome. You can go see Sarah on Mondays. Jerome's Tuesday, Thursday nights. Lots of resources there for you to find out. Okay, that's a good question. Okay, so, but to your question about how we would actually compute this, we want to compute the slope of this line, right? But to compute a slope, we need 2 points, and we only have 1 point. So what we do is we just pick another point that's close, right? So if we pick another point of the function that's close by and compute the slope between those 2 points really close together, it should be pretty close to the slope that we want. So the way that we pick a close by point is we pick a point that's close to the x value. So here our x value is c equals 2, and our second value is z equals 3. Here is exactly the same situation, except instead of calling this point z, we call it c plus a bit, c plus something, c plus h. Some people have called this h delta. Some people call this h delta x. Doesn't matter. It's c plus a little bit. By the way, when people call this delta, they really are talking about the triangle delta. The change delta is the triangle delta, not the weird delta epsilon delta. So when I say delta in this chapter, it really is the triangle. And f prime of c is our shorthand notation for the slope of the tangent line, and I'm claiming it's approximately equal to this nearby slope. Okay. Now, that's not very magical. That's actually kind of obvious that you could do this. If I chose this point very close to C, then these two would be very close together, and the slope of the green line would be very close to the slope of the red line. What's not obvious is that I could take the limit as h goes to 0. If I take the limit as h goes to 0, we can use our limit techniques to figure out what this is exactly, what that slope is exactly. And that's the magic of calculus. That's what's new from pre-calculus. Just to remind you, there's a Desmos calculator that you can use to play around with these things. I'm not going to open it again right now, but it's in the slides here again if you want to play with it. It's in the resources too. And here's what I just said. The derivative, instead of being approximately equal to, is equal to the limit as h goes to 0 of the slope of the secant line, a nearby secant line. Okay. The derivative is the limit of slopes of secant lines. That's another thing to write on your arm or maybe on your paper. The limit, the derivative is the limit of the slopes of secant lines. And there's sort of a secondary definition. How can I get to that one with the z from this one? What do I have to change? What is z equal to? C plus h. Z is just another name for C plus h. So notice instead of h, which is the distance between C and the other point, we have the distance between C and the other point. Right? If you write this as C plus h minus C, you'll see that it's just h in the denominator. And as h goes to 0, the second point gets close to the first point. C gets close to C. Okay, so you can use either of these two. We are almost always going to use this one, but occasionally that one will come in here. And the second one kind of looks a little bit more like what you remember as a slope, right? Like f of b minus f of a over b minus a. So like intuitively it might make more sense. Okay. But there's another box here, and it looks almost the same as the first box, okay? So in the first box, we're at 1 point. 1 point. Like if I go back a couple slides, like here, this is C, right here. We're computing one slope, and our answer is a number, right? The answer will be a number. So if I go forward, this is a number, right here, okay? This, however, what has changed? The C is now X. So what I'm saying is, I could calculate for any X, and I'm not going to specify which one, any X at all, and whatever X I am at, I'll add a little bit to it, do this slope thing, take the limit, that'll be the derivative at that point X. So now this is a function. For every point X, we get a number. So this is just one number. This is a number for every point X. That is a function. Okay. This is the slope function that you drew yesterday. Okay. You could graph it. It would have a graph. And of course, there's also the equivalent one. But if you look at these four things, it's kind of like letter soup, right? There's a lot of stuff going on there. Don't try to, well, you should know all of these, but you really have to understand what the letters are doing and why they're doing them to be able to remember these. They're really all the same. Okay, so we're going to do some calculations like this. In fact, that's what we're going to do for the rest of the class, is calculations like this, just so that we can do that. If you notice in the orange box, some of you know some differentiation shortcuts. Like you know, for example, that the derivative of x squared is what? Anyone? 2x. Did you see how people just said 2x? People that have not had calculus, don't panic. You just remember that, right? It's not hard to remember that the derivative of x squared is 2x. How did you get that, by the way? 2 comes down. This is literally the whole rule. It's like x squared. To do the derivative, you take the number down and you subtract 1 from the power. You'll find that out later. Okay, it's not hard. But that fact and facts like it will not help you this week. Okay, you could shortcut the calculations we're doing and check your answers at the end, just like you could check them by going to Wolfram Alpha or Symbol Lab, Mathways, whatever all those sites are, right? But it won't help you prepare for the quiz. I guarantee you I will not ask anything on the quiz that gives an advantage to someone that already knows that the derivative of x squared is 2x, right? You're all on the same playing field here, whether you've had calculus or not, okay? So if you know those rules, great. That's going to help you a lot. Not next week because it's retake week, but when we get back from break that week, that's going to be very helpful to you. This week, not so much. There's one other thing. This stuff at the bottom. Leibniz made up this alternate notation for derivatives, where instead of the prime notation, we write kind of a fraction of df dx. And what you're supposed to think here is that df dx is approximately the change in f over the change in x, delta f over delta x. And that df dx is the limit as delta, and delta x is like the h This is like, I don't know, physicists would like to write things like this, probably. It's great. It's a very evocative notation. Instead of thinking of a rise over run, a change in y over change in x, you're thinking about like an infinitesimally small change in y over an infinitesimally small change in x. It's a very suggestive notation. It's very, very useful. It looks like a fraction. This is not a fraction, right? df and dx are not being divided by each other. It's just like all one piece of notation. The other thing that's useful about it is that I can write ddx as in I am going to take the derivative of the thing that is in the parentheses, right? So the fact we talked about earlier was that ddx of x squared is 2x, for example. So I don't have to write x squared prime is 2x, because that gets messy. That notation gets messy. Again, we haven't shown this fact yet, but I'm just using it as an example of how that notation would work. Because this is terrible. You can see all the bad things that could possibly happen with this, right? The prime might get lost. You might think the prime was a 1, right? All kinds of bad things. So we don't typically write this. Instead, we write this. This one makes us happy. The other one makes us sad.
Mine just looks like a mark that you didn't mean to throw.
Right, like, oh, oops, and you had erased it. Yeah, exactly. And so it's fine when it's like here, because it's like in this little notation, but when it's flying around in a calculation, it's generally a bad idea. And different people use tons of different notations for the derivative besides this, putting a dot on top of a variable, all kinds of weird things. We're not going to use those, but get ready in your life. If you see derivatives, people will name them all sorts of things. All right, questions about this is very abstract. I haven't done an example yet. But questions about this abstract concept where the derivative is the limit of slopes of secant lines. Okay, let's see how that plays out. So I have a handout for you. It's got 4 calculations on it. It's exactly these 4 things. It's an example of doing this calculation, this one, and this one. Okay, it's all 4. So here you can take some of these and pass them back. There for you. We're going to start with the first one. And I have the answers to these in the slides. Like I'm just going to show you. If you look up here for a second, here's the problems. I've got these 2 answers. Here's the second 2 problems. I've got these 2 answers. But I want to, at least for the first ones, actually do it on the board, right? Because that's kind of a lot to take in all at once, okay? So I don't usually do this, but I'm going to turn that black so that I can write it out. And you can see that we've got f of x equals x. Hold on, there's a bug over here. Go away. Okay. We're actually doing this fact. The derivative of x squared is 2x. We already know what the answer is going to be. F prime of 3 should be 2 times 3 or 6. That's what's going to happen in this first one, okay? So we've got f of x equals x squared times f prime of 3, using sort of the regular definition. The h goes to 0 definition. I'm just going to copy it from what I remember it says on the slide. I'm going to write it and then I'll, oops, we can talk about it. Okay, this was exactly the definition of derivative, where the derivative at a point is the limit of rise over run slopes of secant lines. I've done one change from the abstract slide. What did I do? I let the c equal 3. Okay. That's all I've done. is I let C equal 3. Okay, so right here. Okay. Now, this has an F in it. I don't even know what, do I even know what F is? What's F? X squared. You know what it is. That's the whole point, right? I'm going to be computing the derivative of that function. And just to be really, really clear what's happening here. Here's the function. Here's the point 3. We're computing the slope of this line. And we're thinking that it's going to end up equaling 6. Okay, so, spoiler alert. The answer, when I'm done with this horrible calculation, is going to be 6. Okay, that's what we're computing. Okay, you told me that the function is x squared. I like to do these by doing the easiest part first. Okay, so I plugged in C first because that was the easiest. H is H. That's pretty easy. I'm just going to leave that there. If f of x is x squared, then what is f of 3? 9. So I can put a 9. I'm actually going to write 3 squared just to be clear where that came from, but it's going to be 9. And then how about, this one's tricky. If f of x is x squared, what's f of, f of anything is that thing squared, right? F of 4 is 4 squared. F of elephant is elephant squared. That'd be dumb. Yeah, 2 plus h squared. I'm trying to say it really fast so you can't separate the 3 plus h. 3 plus h is the input, and we square it. Most common mistake is to write 3 squared plus h right here. That's why I say 2 plus h really fast. Okay, well, think about our limit flow chart. What do? We want to solve a limit. Plug in. We see what happens. Okay. What happens if I plug in 0 right now? Bad. Yeah, I get 3 plus 0 squared minus 9 over 0, which is 9 minus 9 over 0, which is 0 over 0, which is bad. Or in other words, it's indeterminate. It's bad for now. Right? It's not to stay bad. Okay? But we don't know what that limit is when we plug in. So what do we have to do? Factor, cancel, expand, something, right? Algebra. Usually leading to some cancellation if we have 0 over 0. We've trained for this. The book is not random facts, right? You've literally been training for this in the whole previous chapter. Okay, so now we're ready to do this. Do you want me to, you said factor, but I think I can multiply out first before I can cancel anything. So I'm going to get 9 plus 6x at h plus h squared minus 9 over h. Any cancellation?
No.
The 9s. And there's more cancellation, but I'm just going to be really careful about how I write it.
Back to the HR.
That is the carefulness I wanted to do precisely. Thank you. So you don't have to actually physically write this stuff, right? But if you're the type that accidentally cancels things that don't cancel, always a good idea to actually factor the thing out. So you can see that it comes out. And now these cancel. This kind of cancellation never helps. You've got to have this numerator denominator cancellation to clear 0 over 0. Now we finally did that. So we can have limit h goes to 0. I mean, it helped, but it's not enough. Of 6 plus h. Now we have a new limit. What do we do when we want to solve a limit? Plug it in. So we plug this one in. Oh, there's our spoiler, right? Indeed, the answer is 6. Oh, because the h goes to 0.
Oh,
Yeah, that's all. Okay. H just goes to 0. Cool. You just computed your first derivative. Now, yay. Now, honestly, this is not how people compute derivatives in real life. Just like we don't compute limits by doing delta epsilon arguments, right? We have shortcuts. We're going to get to that. Any questions about this? I guarantee you this is going to appear on quiz 8. Like this type of calculation will appear on quiz 8, and it won't be enough just to know the answer is 6, you know? Like I'll ask you something about the calculation, right? I'm not just going to ask you for the answer. Yeah. Oh, like here?
Yeah.
Oh, it is given. So you'll be given this. And given some function and a point, we're also given 3. I'm just plugging it in. I plug the 3 in for the C, I plug the function in for F, and everything else was just solving a limit.
Where it's like, because there's the first box, which is this one, and there's the second box that was something that was just.
Ah, yeah, let's go to the second box. Well, let me make sure there's no more questions about this one first. Okay, so that is the first one on this sheet, okay? That's the first one on the sheet. What's different in the second one? An equation for f of x. So I'd like you to talk with your table about that one for a minute. We found this, by the way. You're now finding an equation for the whole thing.
Everything.
Everything.
Right, remember the other.
Oh, that's a good idea.
F of X minus F of H.
Anyone need help?
Other one. Other one.
Okay.
Yeah, the Z one. Wait, got it. Got it. Yeah, I know. Yeah.
So you're doing the second one with an X. Let me give you a hint. I'll do it right on top of this one. Three is X. So now instead of 3, you have X, and then go with that.
But you're using the first one, right?
Yeah, use it.
Yeah. Well, I thought you were using the first one. Like if it's this one, like if it's this one.
Z is X, Z plus H.
All right, let me stop you there. So you're doing the same exact calculation, but you don't know the 3, okay? Now, if you look at your first calculation, you could have done that with a 4 and the same calculation would have worked, right? You would have had a 4 everywhere there was a 3. This would have been a 16. This would have been an 8, right? This here would have been an 8 from 2 times 4. This would be an 8. This would be an 8. This would be an 8. Okay, so I just argued that at 4, we should have like 8. Okay. I could do it again. I could do it as 0 and plug in the 0 for the 3. I could plug in -10 for the 3, and I could get a lot of different answers. But we might as well do them all at once. Let's just not specify what the thing is. We'll just call it X, and we'll run through the whole calculation holding on to the X. So these are X's. These are X's. Guess I should actually erase the 3s, or it looks crazy. Let me look a little bit less like a crazy person. X, 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 X. Let's see what happens if we plug in 0. We get X plus 0 squared minus what? What would this be? X squared. This is complicated because there's 2 letters. Okay, But we're not changing the x, we're just gonna leave it. It's the h that's going to 0, not the x, okay? So the h goes to 0, here we get x squared minus x squared, still bad, okay? Doesn't matter what we plug in for x, it's gonna be bad. X would be 10, 4, 0, doesn't matter. Okay, let's redo this one. When I expand this, I'll get x squared plus 2xh plus h squared. So this is actually an x squared. This is actually a 2xh. And this is an x squared. Same stuff is going to happen though, right? No matter what we put in there for x, these are going to cancel, which is great. We're going to be left with h times, what's going to be here? 2x. If I factor out the h from this, I'm left with 2x plus h. That's just this. And so here we go. There's my 2x. We're done with our canceling. Same canceling happened here. It's h that goes to 0, not x. So I'm left with 2x plus 0, which is 2x. We just did infinitely many derivative calculations at once. So 5 minutes ago, you did your first derivative calculation. You have now done infinitely many derivative calculations. Yes.
What was the, like,
That's a good question. Just like what just happened? What happened here? I don't know if this will answer your question or not. Is we just did the exact same calculation, but instead of 3, we stuck at x. That's what we did. Just like instead of 3, we could have put 4 in there.
How did you factor out for the 2x8 plus h squared?
Oh, that was me multiplying out this. So what you have is x plus h times x plus h, and then if you FOIL it out, you get x squared plus hx plus hx plus h squared.
Yeah, I just, how do you, like, so you have 2xh plus h squared
Oh,
over h.
this stuff.
Yeah,
yeah.
how did you get from that to that?
Oh, I took this part and I factored an h out of it. So these have already canceled by this point. And I have h here and h here. I pulled that out. This is an excellent question, because this is where it starts seeming more complicated than the 3, right? And what I'm left with is 2x plus h. Yes. Yes. If this had been x to the 3rd power, I would have taken the 3rd power. If it had been the square root of x, I would have taken square roots. So this calculation is going to look really different depending on what function you give it. And look what we just found out. We just found out that f prime of x is the function 2 times x. This one is the slope function for this one. If I took, like, here's a point, like if I took minus 10 or whatever, I get a really steep negative slope. And if I take negative 10 here, I get a really low negative number, right? Here, the slope is 0. And the slope function has a root there. So you actually now computed your first derivative function instead of your first derivative value. Okay. Yes.
So if you have like a function.
Yeah.
Have three slope nodes.
Yeah, like if it was 3 plus x squared, then this would be 3 plus x plus h squared, and this would be 3 plus x squared. Even worse, this function could have been 1 over x,
Yeah, I saw that.
right? And then this would be 1 over x plus h, and this would be 1 over x. You've done that algebra problem a few times because we knew we were going to get to this point. These questions are really good because this calculation is highly dependent on what the function was given to you, right? Like every function is going to have a different derivative, and the algebra you encounter when you calculate it is going to be different. Okay, I want to pull the screen back down to do the second two sort of more all at once, because I think we can handle it after doing this one. But does anyone want to ask anything before I cover this up? All right, I'm gonna leave it here in case does anyone want to take a picture of it? I'll take a picture of it once you're done, if you want. I guess it's not really necessary because it's already in the other thing, but it's slightly more detailed here. So let me take a picture. Let me kind of get far away from this. Excuse me, over here. Just in case that turns out to be necessary. Because whoever's watching this recording is thinking, what has been happening? Because what they've been seeing this whole time is the projector. Okay. There we go. Here's the two calculations we just did. Okay. Now you can see them side by side. You can see that all we've done is replace the 3 with an X. And it's exactly the same calculation. All right, let's go to the next one. Now it's slightly different. Instead of using, let me get back here. Instead of using this definition for the derivative at a point, you're going to use this one. And then you're going to let Z go to X instead of Z going to C. So that's the third and fourth one on that sheet.
So does it all just depend on like which letter they decide to use?
Yes, but honestly, 99% of the time we're going to use these. Okay. Well, right, but I want to be able to do it this way too, because there are times that way is useful. So you do the third one now with this type of form of definition of derivative at a point, and I'll let you think about that for a minute, and then I will show you the answer. Are there extras of this paper floating around? I think I saw a hand that I walked away from too. Someone here have a question?
So for this one,
Yeah.
would it be 3 minus, like when you use this 3 or this 3 minus?
The C will be the 3, but the F is still X squared. So C is going to be 3, but F is going to be X squared. So you should have 3's here. You should be 3's. And then your F in that example is X squared again. And I'm just giving you a minute to see if you can get through the calculation yourself before I show you. Do you want to see? Yeah. Okay. Okay, so this time, here's the definition, but I better not, I can't use this marker on the board. Here's the definition, here's the C's.
Why is this? I thought the C was a 3.
The C is the 3. Because, let me go back for a second. See, it's F prime of C. C is the point that extra point is going to. Just like here, the extra point is C plus H going to C. Now the extra point is Z going to C. It might be helpful to write on your paper, Z equals C plus H, and put a big circle around it on your paper. Z equals C plus H. Because all you're doing is letting the role of C plus H be played by Z. And as Z goes to 3, that's the same as H going to 0. Okay, so this time, notice we get a different type of equation. There's nothing to multiply out. In fact, when you let Z go to 3, you get 0 over 0, but the solution is actually to factor it. It's the different algebra. Same problem, that there's some different algebra happening to you when you factor difference of squares, you get a cancellation. And then you get this answer of 6. This is actually easier than the other one. You know? In fact, if this had been x to the 8, the function, this way actually has a way to do it, and the other way would require a lot of multiplying out. That's the a squared minus b squared formula. A squared minus b squared is, let me write it over here. This. But the a is a z, and the b is 3. So it looks weird. So many rules. Yeah. Difference of squares is a big one. Factor difference.
Why do you plug in C going 3 at
Because that's what the limit asks.
yeah, but it's asking that the whole time. You have done it six
Oh,
times.
that's great. Oh, it's asking it the whole time. Once I get everything plugged in, if I do it here, I get 0 over 0. So then I do the algebra, get a new limit. It's way easier. Then I listen to that question of letting z goes to 3, and I put in the z. Yeah.
Okay.
Other questions about this? This is less important than the other one, but you are still going to need to know how to do this one. We're not going to use this one as much, but you need to know how to do both of these. This is sometimes called the alternate definition of derivative. Okay, so in fact, I bet there's some people who think this is the definition of derivative and the other one is the alternate, right? Just depending on where they're coming from. Okay, what's different in the last one? Instead of z going to 3, z is going to x. Same thing. I could have done this calculation with 4 instead of 3. It would have looked really similar, right? I could do it with -10 instead of 3, or 0 instead of 3, and it would have looked similar. So I might as well just do it with x and not say what x is, and do it for all of them at once. See if you can do that for a minute. It's going to look a lot like this calculation. Yeah, I highly recommend putting a line in your Z's. I heard that just now. If you don't do that already, like when you're in your handwriting, what does a Z look like if you don't put the line? Yeah, listen. So you should definitely put a line through your Z's just for the math. I don't care what you do in your normal life, but in the math, you should put a line. All right, do you want to see? Who wants one more minute? Oh, we have one more minutes. Let's let people think for a second.
I just have a question.
Yeah, go ahead.
Because in this one,
Yeah,
you're writing F1C.
yeah.
Would you still write that here?
I write f prime of x for this one.
Oh, because the other one was a value.
That's right. And now it's just going to be a
The whole
variable.
thing.
So you'll get a function where for every x you get a number. Yeah. Okay. Here's what you get. F prime of x instead of f prime of c, like we were just saying. Now instead of z going to 3, z goes to some unknown x, whatever x is. I have the same definition, except I haven't plugged in 3. My function is still x squared, and I can't stress this enough. Not all derivatives are the derivative of x squared, right? That's just the example we're doing today, right? But we could have this be 1 over x, and then this would be 1 over z minus 1 over x, okay? This could be 3x plus 1, and then this would be 3z plus 1 minus 3x plus 1. Whatever the function is going to go in on this step. If I try to solve the limit now, I get 0 over 0. That's extremely bad. So I do some algebra, I factor, I cancel, get a simpler limit. Let z goes to x, and I'm done. I see a question.
This is the same thing. So it's not all-
Yeah, this is the same problem over and over. That's why they're all coming up. Yeah. Is this one on the homework? I think so. Yeah. Something like it will be. All right, questions about this? Let me go back in time for just a second, because these are the even more important ones. These are the H ones. Questions about this?
So, it's,
Hey, I can't hear. If you have a question, ask me, but otherwise, hold on a sec. Yeah. Yeah. That's fine. And please come to Piazza and ask lots of questions. Yes. Yeah, go ahead. Hey, can you guys stop putting your stuff away just for a second? Because I can't hear. What was the question? Yes, and by these formulas, I mean these. But by memorized, I mean, maybe we should put this on your one sheet, right? Yeah, yeah. I mean, you should know these, but I'm kind of against memorization in general. So, yeah, they're all the same. Yeah, these are the same, but with an X instead of a C. These are the same except with a Z instead of a C plus H. This, oh, with the Z, this one?
Yeah.
Yeah. Okay, so we're almost done. I want to stay on this slide for a second because we're some frantic writing down of slide.
Is the answer Z?
What's that? 2x for the last one. You let Z go to X. All right, so I want to talk to you briefly about the qualifiers. A lot more of you handed in qualifiers. Thank you. I am going to try to do your midterm grades today. They aren't due until Tuesday, but I'm going to try to do them today just so that you can see what your grade is now, so that you have a really clear sense of whether midterm retake week is super, super important for you or not, right? Because whatever that midterm grade is, it's changeable during midterm retake week. It's a lot less changeable after that, right? Because we're done with doing the retake. So please take this seriously, and by seriously, I mean actually review the content from that week before you take the next quiz. You will not magically do better if you just show up and take it again. You will not. Okay, I mean, there's a random chance it could happen, right? But I see a lot of times people come back and take the retake and they get basically the same score they got the first time, right? Don't let that happen to you. You got one shot. Yeah. I believe that all teachers do midterm grades for Tuesday if they comply with that rule, and they only have to do it for freshmen. That's my understanding. Nothing happens to me if I don't do that, as far as I know, and I'm pretty sure the other instructors also know that. And so I think sometimes they don't do it. Some classes don't lend themselves to that. Like it's hard to know your grade in the middle. But if they can, you should get midterm grades next week. Yeah, but you'll see yours in Canvas probably tonight. Like a new column will open up, or for you, a new entry in your grades, and you'll be able to see what I think your midterm grade is right now. Okay, because remember the Canvas number, a robot made that, right? He doesn't know, right? But it's probably close, and I'll tell you what I think it is. Okay. Okay, good. Bye. Thank you. Bye-bye.